This is from the workbook. This is Unit 3, number 11, and it is the writing of an equilibrium constant. So it's an equilibrium constant for constant concentration. You're given a reaction, you're given data. So we're told that methanol as a gas is in equilibrium with carbon monoxide and 2 hydrogen gas. Depending on which version of the answer keys you have, there may be a typo in the answer keys for this one. We're asked to calculate the equilibrium constant from concentration, Kc, and the data is for 373 degrees Celsius. We're also told that the number of moles of carbon monoxide is 0.128 moles. The number of moles of hydrogen is 0.155 moles, and the number of moles of methanol is 0.244 moles. The volume of the container is 10 liters. So the first thing that we notice is that we're given number of moles, and equilibrium constant from concentration must be determined from concentration values. So for each substance, we need to take the number of moles and volume and work out its concentration. So the concentration of the CO is equal to its number of moles divided by volume, 0.128 moles divided by 10.0 liters, or 0.0128 mole per liter, or molar. So similarly, the concentration of the hydrogen is the number of moles divided by 10 as well, to 2 sig figs, so 0.0155 molar, and the concentration of the methanol is 0.00244 molar. So the equilibrium constant expression now, Kc, we know Kc is written products over reactants, so concentration of CO, gas, multiplied by the concentration of the hydrogen, and because the coefficient of hydrogen is 2, we know that that's squared. We also divide by the concentration of products raised to their coefficient squared. We have only one reactant, CH3OH, methanol, and it's to the first power because its coefficient is 1. So to work out the numerical value for Kc, I put in the concentration values for each of the reactants and products. So the CO would be 0.0128. And this is one of the rare occasions where units don't matter. We don't express units for the equilibrium constant, so we don't need to put them in. 0.0155 squared and divided by 0.00244 molar. And I got 1.26 times 10 to the negative 3. So a couple of observations. First of all, this was a homogeneous equilibrium. All of the reactants and products are in the same physical state. So all of the reactants and products get included in the Kc value. In a later video, I'll show you one where we have a heterogeneous equilibrium. In this question, after we do this calculation to get the value of Kc, which we know is only valid at 373, equilibrium constants are always temperature dependent. They're only valid at one particular temperature. So once we've done all this, then we're asked to say whether, in part B, reactants or products are favored and why. So in part B, we can look at this value and say, so for part B, we can say that we have a very small number here, less than 1. So that tells us that there's mostly reactants, or reactants are favored at equilibrium and there's less product. So reactants favored because Kc is less than 1. In part C, we're asked to determine Kc for the reverse reaction. So normally we call that Kc prime. So Kc prime is simply the reciprocal of this value. So Kc prime is 1 over Kc, or 793. Because if we wrote the reaction in reverse, we'd simply change our notion of reactants and products, and it makes the equilibrium constant for the reverse reaction the reciprocal of the forward. So it's pretty straightforward to calculate Kc for the reverse reaction.